Hi, for the second part of this lab 5, we're going to make a 2-bit synchronous counter, okay? A 2-bit counter is basically a circuit that has 2 bits of memory, that is the flip-flops in this case, and it'll count up, that is, it'll go 0, 1, 2, 3, 0, 1, 2, 3. And here is a simulation of it. Okay, let's see. See, there's, first of all, there's an asynchronous clear input. When I say clear, the count should be 0, 0. So I say clear, and the count is indeed 0, 0. And the clock can be disabled on this simulator, right? So that will disable the clock so that if I run the clock, nothing happens to the count. But if the clock is enabled, right, then when I count, when the clock goes up, you see, the count will go to 1. And when the clock goes up again, the count will go to 2. And when the clock goes up again, the count will go to 3. And when the clock goes up again, the count will go to 0. Okay? So that's how this works. Now, on the real circuit, we'll be using a chip called the 7474, which we have in the lab. This chip has 2 flip-flops. However, these flip-flops don't have enable lines. You could make an enabler or disabler for the clock by putting the clock input into an AND gate, right? And however, you don't have to do that. You just have a clock that's always enabled. That would be fine with me. It's up to you. But anyway, that is the chip we're going to use. And the circuit will have the 7474 chip with the 2D flip-flops there. And down here is your 7486, which you've used before with the exclusive OR gates. We'll need one exclusive OR gate. Well, anyway, first of all, before making that, we'll be looking at the design process for this flip-flop, which will give rise to this one exclusive OR function, for which we'll need an exclusive OR gate for. And you see there, you need an inversion, but we don't need an inverter because the flip-flops have a NOT Q output. Each flip-flop has a NOT Q output. So we can just feed that right into the D input. We'll talk about that in class. Okay.